Excellent. Thank you so much. And thank you everyone for being here. So I'm going to be talking about graphical reasoning, but before we start, I'm going to just kind of briefly acknowledge all of the wonderful people that I've worked with. This slide is starting to get a little unruly, but I've just been very fortunate to work with a lot of wonderful people, and I'm excited to continue new and start new collaborations at UW-Milwaukee. All right, so in line with the goal of this webinar series, I'm going to start with a claim. Scaffolding assessment questions can support chemistry students in drawing inferences from graphical representations. And my goal here is to kind of unpack the different parts of this claim. And I'm going to start with, I'm going to start with the end here, drawing inferences from graphical representations. And I'm not going to spend too much time on this other than to say that we want students to be able to draw inferences from graphical representations. And I think if you're here, you know that's the case. We use graphs across science, technology, engineering, and mathematics. Very useful representations to summarize quantitative information. And we want students to be able to make trends and reason about the processes that we're modeling with these graphs. Not just so that they can, do well in a class and everything, but also so that they can engage more broadly beyond their courses with public health issues and just a broader social context. Looking at the next part of the claim here, support chemistry students. Now, of course, students need support. Chemistry is a challenging topic, but this is where the research comes in. So by collecting data and by analyzing and characterizing students' reasoning, we're able to provide insight regarding specific targeted ways that we can help students learn chemistry. So I'm going to provide some evidence from some of the previous research projects that I've been on that has focused on students' graphical reasoning. And part of the challenge, if you just kind of think about a general chemistry course, students encounter a lot of different types of graphs. You have concentration versus time, you have distribution graphs, you have reaction coordinate diagrams. But part of the challenge here is that each of these different graphs are intended to be read slightly differently. So the way that you read a concentration versus time graph is different than how you might interpret a distribution graph or draw inferences from a reaction coordinate diagram. So here we're just going to kind of talk about how do students interpret these different graphical representations. This is a concentration versus time graph. And the data for this comes from a paper that we published in 2019. It involved undergraduate students. They were in first year general chemistry course. And on an exam, they were provided this graph and asked at which time point was the rate of the reaction the highest. And you can see that there are different points here, time equals 1, 5, and 10. And if we look at a student response here, this is Nancy, answering on the exam. She says the reaction rate was greatest at t equals 1 minute because the slope of the curve is the steepest there. The reaction rate is the lowest at t equals 5 minutes because the slope is the smallest there. And so here, Nancy is kind of focusing on that shape, kind of the slope, and drawing inferences about rate. And I'm going to be talking about this, what I'm calling here, just an intuitive idea about a graph, just idea that steepness provides information about rate. And this is a really productive idea. And we see Nancy here interpret the graph and was able to draw the relevant conclusions that we wanted. But the problem comes when students kind of take this idea and then try to apply it to a different context, to a different graph but it's less productive. So for example, a distribution graph. And to provide a little bit of context, this is from a different paper published in 2020. And here we interviewed students, and the students were undergraduate students from a first year general chemistry course. During the interview, students were provided this graph here. And for context, they were told that the graph pertains to a sealed flask of neon gas, and that the flask was at constant temperature, constant pressure. So here we have number of molecules versus speed, and students were just kind of asked to generally interpret it. How would you describe this graph? And I will let you read that. Hopefully you've had some time to read through that. So if we just kind of focus on the beginning of Jacob's discussion here, it's kind of like he's interpreting the graph more as a process. So we want students to view the distribution graph as, and kind of interpret it almost like a histogram, where that peak is providing information about related to the average, or kind of a measure of central tendency. But here Jacob is talking about kind of tracing the graph. As x increases, or as x increases along the x-axis, as x increases, or as speed increases, y increases, kind of implying the number of molecules, how many molecules are in this container, depends on the speed that they're moving. And some of the students, when they were in our interviews, when they were describing the graph, kind of took that a step further and wrote out a reaction to kind of explain how they were reasoning about this process. What might explain why it seems as though the number of molecules is kind of decreasing over time. So we have two neons that are reacting together and forming this kind of neon 2 compound. So viewing the graph more as a process, with the peak being an event, and then number of molecules are kind of decreasing there. If we focus on the second part of Jacob's discussion here, he's focusing largely on slope and the shape. And this is similar to what we saw with the previous student, Nancy, with the concentration versus time graph. Reasoning with this intuitive idea that steepness provides information about rate. So we have a sharper increase, and then you have kind of this tail end here that drops off, and the rate is more constant.
Hi.
And with this discussion here, there's almost this implicit mapping of time onto the x-axis here, right? As the student is kind of talking about the events and the molecules kind of disappearing, we have this implicit discussion, or this implicit mapping of time onto the x-axis here. And if we think about, let's say, a different representation, here we're talking about a reaction coordinate diagram. And to provide a little bit of context, this was a different study that we published in 2020, involving interviews with first-year undergraduate students in a general chemistry course. During the interview, students were provided this reaction coordinate diagram, and they were provided this information here on the side. We have a reaction. It's going from A to B, and then we have the proposed mechanism. And you can see here that it's a multiple step mechanism. We have step 1, step 2, step 3, and rate constants associated with each of those steps, with the rate constant for step 1 being less than the rate constant for step 2, but the rate constant for step 2 is about the same as the rate constant for step 3. So this is the information the students were provided. And as kind of a general question, how would you explain what's going on in this mechanism to a friend? So just kind of explain what we're observing here. And as the students were, as we were interviewing the students, we encouraged them to draw, to explain their reasoning. And this is what Beth drew. We can see some of the features. We have the y-axis as potential energy. We have the x-axis being the same, reaction progress, starting with a higher initial with A and ending with a lower B here, lower in energy. And then we have the 3 peaks corresponding to the 3 different steps in the mechanism. The interesting part here is if we look at how Beth was thinking about how to draw this, we have X to Y, which is the second step here, and Y to B, which is the third step. We have Beth talking about how the slopes are equal, which is kind of how she's thinking about this right here, where K2 is similar to K3. And then for Y, for A to X, which is the first step, saying that the slope there is smaller, which is kind of how Beth is thinking about K1 being less than K2. So similar to what we saw with the other students, where the student is focusing on a slope. And the interviewer here asking a follow-up question, what makes you focus on the slope? Beth replies, just because I relate slope to basically speed, and just a steeper slope means that it's proceeding quicker. How do you know that? Was that something from the course? And then Beth kind of talking about how maybe she picked that idea up from another class, or she's not quite sure. But similar to what we saw with the distribution graph and with the concentration versus time graph, we have students that are using this idea, steepness provides information about rate, and then kind of applying it across these different representation types. And as part of that, similar to the distribution graph, there's this implicit mapping of time onto the x-axis. And this is particularly a problem for reaction coordinate diagrams, just because of the way that we use them in large enrollment courses like introductory general chemistry or organic chemistry, where we're really just focusing on that vertical distance, that horizontal kind of x-axis is less relevant. We're really interested in that difference in energy there. And so this is less, I mean, it looks like a graph for sure. We have 2 axes, but it's more useful to think of it as more of a qualitative tool or a diagram instead of a graph. But students are interpreting it as a graph because of how it looks. So if we kind of revisit our discussion here, how do students interpret graphs? They have these productive ideas for interpreting graphs, and the challenge is knowing when those ideas are relevant. But we have this idea of steepness as rate across these different representations with this implicit mapping or this implicit association of time with the x-axis. And I want to make a disclaimer there. Students are talking about rate, but as a mathematical concept, rate doesn't have to involve time, right? You could have a ratio of any 2 variables, but often our just general experiences that we encounter related to rate, it often involves time, like, I don't know, miles per hour or something. There is this implicit association with rate and time. And as students are kind of describing the process of reaction coordinate diagrams and distribution graphs and reasoning about steepness as rate, it is associated with this time component. So given that's the case, given our research is telling us that this is a specific way students are having difficulty with these representations, one of the possible ways that we could support students is providing scaffolding assessment questions. So what is a scaffolded assessment question? Well, so scaffolding could refer to a lot of different activities. Here we're talking about providing additional support or additional assistance to support students. And one of the important features here that I'm going to really emphasize is using scaffolding as a way to direct students' attention to the specific relevant features that we want them to attend to. And some of the ways that we could do that, drawing on prior work, Ralph and Lewis talk about the utility of using multiple different representation types. So the context here was stoichiometry. Rather than just providing the text, the prompt there, we could pair our assessment questions with different types of representations, and maybe even more than one. So a symbolic representation of the equation, the particulate equation, and some kind of organizing matrix like a table here. And each of these different representations have a way of focusing students' attention to specific relevant features, like the table, emphasizing moles and ratios and those relevant numbers from the prompt. Other ways that we could support students through scaffolding, case comparisons is something that's been used quite a bit in the context of organic chemistry reactions. This is a paper by Watts and colleagues. And here we're talking about problems that involve essentially side-by-side cases or these different examples. And it's the differences between those two examples that kind of naturally encourage students to make comparisons and attend to specific relevant features. So this is an example here, two different reactions. One reaction is faster, one reaction is slower. And we could ask, well, why is one faster than the other? And there are different features that you kind of naturally attend to. And those are the features that are different across the two examples. Maybe it's something related to the starting material, or maybe it has something to do with the reagents, the nature of the base or the nucleophile that you're using that could influence the speed of the reaction. This is a paper by Noyce et al. It's a really great example of designing scaffolded questions. What I like about it is they talk about kind of the iterative nature of writing an assessment problem. Sometimes it takes multiple tries to kind of see what works and whether or not it's supporting students in the way that you want it to. So what this might look like on an assessment question. This is a paper we published last year on an exam. Undergraduate students were provided this graph, and they were asked to circle the point on the graph where the rates of reaction 1 and reaction 2 are the same. So this is one of those instances where we want students to use that productive idea of, steepness provides information about rate. But here, that wasn't the case. Walter says at point E, both reactions have made the same product in the same concentration product in the same amount of time. So rather than attending to the axes, Walter is really focusing on that salient feature here, that intersection. And something is the same there at the intersection. It's just that it's not rate. And so we're seeing something similar to the previous problems where we want to direct students' attention to important information related to the axes. So if we look at a student who answered the question correctly, that could provide some suggestions about how we might scaffold the question. Here, the student starts off by talking about a definition for rate. It's concentration of product over time, which is essentially the slope. And then they talk about how the slope is the same for reaction 1. And then if you draw a line here tangent to this curve, then you have the reaction rate being the same. So one way we could potentially modify this problem, and it's a relatively easy change here, is first asking students to provide a definition of reaction rate. And that will then get students to start thinking about, well, what is a definition of reaction rate? Well, it's concentration over time. And how does that relate to the problem here? Well, that's the ratio of the two axes. And with that, I'd like to end with my claim here. Scaffolding assessment questions can support chemistry students in drawing inferences from graphical representations. And I thank you so much for your time, and I would be happy to answer any questions that you have.
Thank you so much, Jon-Marc, for that. Thank you. Thank you. So I invite anyone inside of the audience to raise their hand. You can raise your hand with the little reactions and ask your questions. Or if you feel more comfortable typing them into the chat, you can do that as well. And I'll read your questions out loud. All right. Nice. We have our first question. You can unmute yourself and ask your question if you wish. Safa?
Oh, sorry.
There we go.
Okay, sorry. Hi. Thanks for your presentation. My question is, you said that scaffolding helps students, and you did a very qualitative, so small sample. Like, do you have like post-assessment or like some like evidence that like those results like panned out?
That's an excellent question. The short answer is no. The longer answer would be me directing you to some people that have done that. And that a good example of that would be this paper right here by Noyce and colleagues. And they do this really iterative design. I really like the way that they frame it. Essentially, they make a change to the exam question. They then collect the student responses and they analyze it. And then they see, okay, well, how did students respond in that context? Okay, that didn't quite get us what we wanted. Let's make another change. And so they kind of do it very systematically. And that would be a good example of the influence of scaffolding on student responses.
Okay, thank you.
Great question. I see there are also some questions in the chat, but I'll let Nikita decide who kind of goes next and everything.
Okay. Vicente's hand is up, but I do want to get to this question that is in the chat. So David said, would these students have had any prior instruction as to how to interpret these different graphs? Because that is because they are such different chemical subjects.
They really are, and that's a great question. So the students, just to clarify, the students, they are different students across the different samples. But whenever we do these types of studies, just typically we'll interview the students or we'll assess the students after they've learned the context. I didn't mention that, but yeah, the interviews take place after, so for example, the interviews related to reaction coordinate diagrams or distribution graphs, we interviewed the students after they took their exam on that relevant topic, after they've discussed it already in class.
Vicente, I think your hand is up. You go.
Okay. So I'm going to use my question to elaborate on the idea of the webinar so that maybe more people feel free to do so. When we thought about this series, we wanted the presenters to make a claim and then present a rationale to support their claim. And then we said that we were going to poke their claim so that and their rationale, that we were going to try to find review to things that they may have said, just to engage in more arguments. So I'm going to present my first kind of question. When you presented some of the scaffolds, one of the scaffolds was to present different types of representations. I have to wonder, isn't that going to create just more problems? Isn't now that I have to deal with several representations that the students have to understand, and you have their graphical but you have visual you have tabular representations, you have symbolic representations, and each of them may be quite complex to decode. So really?
Yeah, that's a great question. Thank you for asking. So in the context of this paper, what they did was they essentially were looking at the effect of different combinations of these different representations. So it would be the case, and you would expect there to be a difference if you did text plus symbolic, text plus particular, text plus table. And if I remember this paper right, what they found was that the table was the one that supported students the most. So maybe what you're kind of describing with, now you have this new representation that students are struggling with. Maybe there are some issues related to interpreting particulate diagrams that might have been difficult for students, or interpreting the symbolic representation. But as a way to kind of organize the relevant information, the tables seem to really help as a scaffolding tool.
We also invite any more questions. So I do have a question. How do we know, in terms of like scaffolding, I know the whole goal is to get students to then understand and not form misconceptions, but how do we know if we've like scaffolded too much to the point that if we do give them like a question, they won't be able to handle it because they're so used to like training wheels per se?
So is your question kind of like what happens when you remove the scaffolding? Is that kind of?
Yes.
Yeah, so that's a good question. And the phrasing scaffolding is intentional in the sense that scaffolding, if you think of like building scaffolding, it's intended to be temporary. And there's this idea of over time, slowly kind of fading out the scaffolding. The specific, what is the appropriate way to fade out scaffolding is probably topic dependent, and it would be a really interesting study to do. But the idea is that maybe at the beginning, students have more scaffolding, but by the end of the course, when they're taking a final exam, maybe they don't need that scaffolding anymore, because at this point they know what features to attend to, and they know they've kind of developed that expertise.
So there's another question in chat. Stephanie says, how do you think the concept being modeled affects the graphical reasoning the students may engage in? For example, do you think that students thinking of a phase change modeled in a line graph might be cued in the steepness of the line in comparison to a kinetics context?
That's an excellent question. And yes, so I could pull up a different presentation. So I'm working on a collaboration with, let's go to our thank you slide. I'm working on a collaboration with a mathematician, Stephen Jones. He's at BYU. And one of the things that we're interested in are just kind of characterizing all the different types of ideas that students associate with different graphical patterns. And it is very context dependent in the sense that it depends on the specific shapes, right? So if you have something like, I'll go to the very beginning. If you have something like these graphs, we're kind of limited by the shapes available. And so for this one right here, that's a straight line. We have a lot of evidence to indicate that students are going to associate the idea that straight means constant. Something is constant because it's straight. This right here is straight, so something is constant. This right here is straight, so something is constant. So the specific shape has a really big influence on the specific ideas that students are associating to the shape, and with less of an influence or less with less emphasis given on what the actual axes say, really just kind of thinking about the shapes. Hope that answers your question.
Yes, I hope so. Let us know if it did, Stephanie. Yep, thank you. More questions? Go ahead, Vicente, and then Elena.
So many of the things that that you have described in my mind can be mapped to heuristic reasoning. It is the students are just paying attention to salient features, what is easier to process the fastest, building quick associations with what they already know or have experienced, and using what is called attribute substitution. That is, well, I know how to think about time. Let me think about time. So the question is, many of the people that work with heuristic reasoning would claim that the best way to help the students is to engage them in some type of metacognition. So that they are much more aware of this kind of very system one type of thinking that is going to typically override analytical reasoning, if possible. So to what extent do you think that this scaffolding that you propose to do has to be more targeted to metacognition than to actual cognition?
Yes, that's an excellent question. I think that it could vary on depending on the task that we're focused on, or depending on the context that we're focusing on. And I don't have a lot of experience in the metacognition realm, but you could definitely design a question that is aimed at metacognition. And that still kind of falls under the scaffolding umbrella, and it would have, I would imagine it would have the same result of, okay, now we're getting students to reflect on their reasoning, and rather than just kind of attending to those salient features, they're kind of taking a step back and thinking, they're kind of taking a step back and they're thinking what we want them to, or they're focused on what we want them to focus on. So just going back to this question right here, if we think about how it could be phrased in a way that is maybe more metacognitive as opposed to just like define reaction rate, I'm trying to think what that would look like as a metacognition suggestion. Maybe it would be something like, I'm not sure what that would, maybe it's just more broadly asking students to reflect on their answer and whether or not their answer is, like consistent. I'm not really sure what that would look like, but I could imagine some kind of prompt where instead of asking them, to provide a definition, that you're asking them essentially to think about their answer and if it makes sense. I don't know if that answers your question. It's kind of a roundabout way of saying, I'm not sure.
Can I go?
Yes.
Okay. So my group thinks a lot about how students engage with empirical data. And one of the things that I noticed is that a lot of the data sets we use seem a bit messier than some of the representations that you used. And I'm wondering, related to this question about heuristics, how do you scaffold so that students can handle the mess? So how do we tailor their attention to the things that are important and move their attention away from surface features that can be really distracting?
So does this kind of get at more of like a nature of science type question where I guess it depends on what, as a follow-up question, what do you specifically want students to focus on? Is the whole idea that you want them to recognize that we don't have straight, clean lines. We have some kind of noise there. Is that what you want them to focus on, or what features, I guess, would you want them to focus on with this kind of more realistic data, I guess?
It totally depends on the context we're finding. But if students are using these graphical forms that you're talking about, what happens when the form isn't so clear?
Okay, right. So instead of a line that looks like this, maybe it's a little jagged or something like that. So it's kind of interesting that you should say, because so the project that I'm working on with Stephen Jones here, we provided students a bunch of different types of graphs, and some of them were more like realistic in the sense that they had they weren't perfect curves. And one of the graphical forms that we ended up talking about in that context was students were talking about how, because it wasn't a like clear, perfect line, they were saying, oh, this is more realistic. So I think that the students recognize that a perfect curve is idealized, or a straight line is idealized if it has some kind of jagged or this kind of like this motion to it. It is some kind of data that were collected. So I think students are recognizing that aspect of the graph, and I don't know if you've noticed, does it seem like students are uncomfortable with it not being perfect?
We have definitely seen some of that, but we've also seen them attend to very unexpected features of the data. So, and that's why I haven't figured out how, from a scaffolding perspective, to prevent that. Like, so for example, Stephanie, who asked a question earlier, I mean, we had a graph where we narrowed everything in our question. We narrowed which lines to look at. We grayed out the lines that weren't relevant. We narrowed down which concentrations on the x-axis to look at. And we still had students latching onto features outside of that in the data. So yeah, I don't know what the answer is for narrowing focus when the representation's a bit messier.
I see. Yeah. Yeah. I wonder, just even taking a step back and some kind of case comparisons where you're showing like a kind of a messy curve and then one that is not messy. It's like, how are students thinking about those, and why is this one messy? Is that okay? What is more realistic? That type of thing.
I love that.
So we have two questions. First, we have one in the chat, Elizabeth, and then we'll get to you, Teresa, and then Safi as well. So Elizabeth in the chat asks, can you comment on similarities of how students use graphs and equations, maybe with a reference to heuristics just mentioned, and any surface features?
Boy, can I. Let me dive into some of the hidden stories. So a lot of the work that I've done has looked at students' graphical reasoning. Oh, I don't have that slide here. But the main idea is, if we just kind of think broadly about what I've been talking about with students' graphical reasoning, where they're focusing on some kind of graphical pattern and they are assigning this idea, this framework of viewing students' kind of intuitive ideas about graphs is essentially an extension of another framework that focuses on how students reason about equations. And so maybe I can send you that reference, but it's work by Bruce Sharon's Symbolic Forms. The whole idea is that there are specific patterns in equations, and students associate ideas with those surface features. For example, if you have something like y equals mx plus b, that is a very common graph, that is a very common symbolic pattern. And students might have productive ideas that they would associate that. There you have some kind of initial base that is then altered by another value. Or just the idea that you have one value on one side, another value on another side, separated by an equal sign. And that kind of pattern means identity, or that kind of pattern means equilibrium or equality. So there's definitely the symbolic analog to kind of associating intuitive ideas with graphs. It's just instead we're focusing on associating ideas with equations. I could, as I'm answering the next question, I could maybe find an example of what I'm talking about, but yeah.
Teresa, you can move forward with your question.
Awesome, thank you. I have a question, since it seems like when you are showing students these representations with a graph, they focus on the shape of the curve and like block everything else out. I'm curious if, because it seems like the setup of the question is you give a graph, you give them the axes, and you ask them for an interpretation of some sort. Do you still see the same misconception if you gave them a blank graph, an interpretation, and asked them to draw the curve?
Yes. So I can pull up. We saw something like that here, and it was kind of interesting. So if I have your question right, essentially asking students to draw a graph or kind of construct a graph as opposed to having them interpret one, is that kind of?
Yes.
Okay, yeah, so for this paper, this was kind of a fun one. In an interview context, undergraduate students were asked to draw a graph of rate versus time. And we definitely saw students thinking about that in a different way. So they were using these ideas about, like steepness provides information about rate, but part of the challenge with this is that here, if it's rate versus time, steepness doesn't provide information about reaction rates. Steepness is going to provide information about the change in the reaction rate. And so we got some interesting shapes. And with this, we had students who were kind of essentially had these very different shapes, but their descriptions sound kind of similar, where they all kind of say that it starts high and then it slows down and then it kind of plateaus. That's essentially what each of these are saying. But you have these very different shapes. And part of that is just, I guess, how they're operationalizing rate. Is rate kind of like that vertical position, or are they thinking about it more as slope? So you have these different ways that students were trying to apply that kind of intuitive steepness provides information about rate, but it was kind of further confounded by the fact that the y-axis was reaction rate.
Thank you.
Yeah.
Safa, you can unmute yourself and tell us your question.
Yeah, my question actually relates more to the scaffolding piece. So I was just curious if you had any insight, because I'm very interested in scaffolding and have worked to redesign some activities with more scaffolded questions. But it seems to me that there's this balance between too much scaffolding, where you're pretty much giving it to the students, because to some, it seems like some of the struggle, like, that's beneficial to students and it helps them to learn. But like, do you have any insight as to like, where's the balance point in applying scaffolding?
Yes, and that is a wonderful practical question that is really relevant. And the answer is it depends on the context, and that's what makes it so difficult, right? And not only the context as in like the topic, but it depends on the students that you're working with. So the type of scaffolding that is appropriate for some kind of like preparatory course where this is the first chemistry course they've taken and they don't have any prior chemistry experience. That scaffolding is going to be different from maybe an honors chemistry. So there's a lot of layers of context, which is not a great answer, but my general suggestion is just that it takes time to kind of develop that balance. And that kind of gets back at that iterative nature of, okay, this worked. Okay, that was way too easy, or something like that. Collecting your own personal data and making changes based on that.
Thank you.
Yeah.
So I guess kind of walking into that question, I guess from a practical standpoint, developing scaffolded items could be very like time consuming. How would that then work? Or how could something instead, for example, like practice problems, giving students a bunch of multiple practice problems, how would that work then instead of scaffolding and working to scaffold these items?
Yeah, so yeah, the repeated practice. I think that my first answer would be that you could do that, right? So having the students do multiple practice problems, in general, repeated time on task is going to support students and going to help them develop expertise. Students are working on the problem more and more. That's good. So, I mean, it doesn't necessarily have to be an either or. You could use repeated practice and then also do scaffolded questions, but it does take time to develop those types of questions. And then maybe that kind of gets at a bigger question that is, what are the learning objectives, or what do you want students to be able to do by the time they leave the course? So is it that we have these exercises that we want students to be able to do, and so we provide them lots of homework examples, and then we have an example, or we have a problem that's kind of mirrors that on the exam, and they're able to do that problem and it's great? Or is it more on an exam is the expectation that we want them to be able to grab different ideas that they've learned from the course and kind of bring it together? Maybe a more complex problem like that would require more scaffolding.
Vicente, can unmute. There you go.
Listening to you, I was thinking that in principle, I have heard you describe two types of scaffolds in my mind. One is, okay, I guide the students to build things step by step, so that I direct them more in the direction I want them to go. But there could be also scaffolds that have to do with making them reflect on what may be relevant versus irrelevant in thinking about this presentation. So that is more, again, more in the, okay, how you think about this instead of what specific things you have to think about. So what do you think about what could be more effective, how to help people recognize how to think about it, or to guide them in constructing the correct answer?
So if I understand your question, so you're talking about two different types of scaffolding. Are you talking more one scaffolded approach is very specific to a problem and the other is more kind of skill-based, or could you kind of clarify?
It's not that I have it clear in my head. It's just based on what you have been saying, is that it would seem that there's scaffolds that direct me to think the way you want me to think for that particular problem, or not. That you have to think about what is the rate of the reaction, and then maybe how they're related to the slope, and then, oh, pay attention to the slope. No, so that would be like very directive.
Yeah.
but there's also, I mean, the fact that when we develop expertise, we develop the ability to recognize how to think, no, how to recognize relevant versus irrelevant features in a graph. No, so I mean, an expert directly goes to the relevant, and while the novice is going to be lost between the relevant and the relevant features. It's expected. But how is that we help the students to develop this expertise more quickly? That is not just based on repeated practice. That's a way of doing it. But are there any other ways that are more direct in which we can help the students reason about like general types of problems or general types of graphs or general types of equations? I'm just was wondering if there are other ways.
Yeah. So it sounds to me you're kind of thinking, how do we teach students how we think, right? How chemists think. As far as more general principles, we could, we can model how we interpret graphs as instructors. So when we're teaching it, when we're kind of teaching and we're presenting on this specific, introducing this specific type of graph in class, we could be explicit about kind of what we're thinking. What are the features that I'm focusing on? How would I personally interpret this graph? So, I mean, whenever I interpret a graph, I always focus on the axes because, I mean, the context and the information coded there is really relevant. So those kind of more general practices, and maybe that to some extent gets at your metacognition, your metacognition question about kind of reflecting on our own practices and the practices that we want students to adopt. Like, okay, let me start. Let's first interpret, let's first look at the axes. Okay, it's this and it's that. So I mean, as far as what that might look like on an assessment, typically scaffolding on assessment tends to be specific to that assessment question, and it's very goal directed as opposed to more kind of developing that skill. But in other contexts, you know, when you're introducing the material and when you're teaching, unpacking those, how an expert thinks, how a chemist thinks, and what features they're focusing on as general rules, be a useful practice.
All right, we're at the 7 o'clock mark, at least 7 o'clock Eastern. So I would like to thank Jon-Marc for talking to us today, opening our eyes about scaffolding and inside of graphs. Also like to thank Alina and Vicente, my co-hosts. You guys are like coaching me forever, so thank you. And I want to thank you guys who are inside of the audience for coming as well, and posing such really good questions. So thank you all.
Can I make a quick comment?
Oh yeah, go ahead.
Thank you. So I wanted to share this just to answer Elizabeth's question there about what symbolic forms are. So I'm just, now this is in the recording if anyone ever wants to look at this, and just there for context with the references and everything. Just the idea that there are these kind of specific templates and students are associating ideas with those templates, and there's a lot of fun literature on that. So I'm just gonna say that, but thank you so much.
Yes, thank you.
Thank you for that, Johnny. I had something come up, so I have to kind of hop off right away, but I'll see you all.
Cool. Thank you so
Yes.
much. Nice chatting.
Yeah, thank you very much.
Yeah.
I'll see you guys as well.